Hey, how y'all doing? Or how are some of you doing? Because it's earlier than normal. Apologize for the changed time. Could one of you unmute and let me know that I can hear you? Which is
I
actually
can
a
hear
weird
you.
statement if you think about it. I didn't hear that at all. So let me try one more thing. That's goofy because I was just in a Zoom room and it was working fine then. And okay, so could you try it again?
Can you hear us?
Damn it. Okay. Well, last try and then I'm gonna give up. Could one of you unmute one more time? Hopefully.
Hello.
Okay, bailing. Okay, I should be able to hear you now, but let's find out. I shouldn't say one. I said just before one last time. Could you try one more time, please?
Yeah. Can you hear us?
Okay, good. So now if someone were to unmute and let me know that they've got a question, I can then hear it and then answer it promptly. Okay, so what I had in mind to do today is the normal thing. Um, Share a screen and then let you know where things are at in a broad sense, in sort of a big picture sense. And then we'll see where we get to today. And I think today and tomorrow, I said yesterday, sort of, I'm feeling flexible with because I want to make sure that we're able to get done everything we need to before the midterm. And to do that shouldn't be bad, but maybe if I start by sharing a screen, it will be the right move. Okay, so yeah, today is the oddball time. Again, for some of you, that's unfortunate. But you know what? The recording is something that works for most people well enough. At least that's what you all told me. And if I'm looking at the syllabus for the class, where we're at is that well, we've finished up chapter 5, sections 5 and 6, a day early. Okay. Um, that doesn't mean you're happy with it or comfortable with it. The material in chapter 5, sections 1, 2, 3, 4, 5, 6 is still something that many of you might say, more comment on, more talk on that. That'd be great. If you want to talk about questions related to exam 2 today to get you ready for it, the exam turns live tomorrow right after class time. We could spend time today talking about stuff related to exam 2. If you don't have questions on that, what I'm going to be doing is moving forward into chapter 6, sections 1 through 3. And there's an associated lab with chapter 6, sections 1 through 3, that is due Monday of next week before class time. Yes, we could talk about chapter 6. And no, I don't want you to focus on it. What I would rather you focus on is um, getting ready for the test. The test is turned live Thursday, right after class, due Saturday by 11:59 p.m. So they always say give, students at least 24 hours. So we're going to say let's go for 2 days plus a few hours. Uh, 20, 48, 55 hours to get the test done, basically. Okay. So as far as I know, then it'd be a good idea to sort of go back to where we're at and the Wednesday, Thursday portion of class today. Want to note the material. If you want to talk about quality control, I'm happy to do it. If you don't have questions on review problems from most likely chapter 5, we'll go into new material. However, there is no video from 2024 on that chapter 6 content. So this video will be the only one that you'll have access to. That 2024 class, we didn't do chapter 6. Oh well. Okay, so that's my administrative list of things to mention. Do any of you want to ask questions about something administratively? Okay. Then I would love to then say if you have any questions from the sample exam, or any questions related to chapter 5, sections 1, 2, 3, or 4. And those problems, I believe, are all due tonight. We could spend the whole class sessions talking about homework related questions if that be your wish. Okay, so I do want to mention then we're going to sort of do new content today, chapter 6, and there are some discussions of homework related and exam related questions here in a video from 2024. We did spend most of a class session talking about reviewish material. So my goal today is to get you set up for the lab on chapter 6. Same lab groups as earlier in the week. However, there is only one lab in the second part of the week. Again, I want you to spend a bit of time prepping for the exam. And this quality control lab, you could start it today, you could start it tomorrow, you could start it on Monday. As long as you get it done before Monday at 4 p.m., we're all good. Last call for questions. Or we're moving into newish content, chapter 6. So chapter 6 is it feels like a real strange diversion. And the reason is in our book is there are an awful lot of engineering programs out there that say, oh, we need our students to learn about statistical process control, or if you will, control quality control, or sometimes called control charts. We want our students to have seen this Six Sigma concept. Cool. That's a requirement. So we're putting it in stat 312. The idea behind statistical process control actually ties nicely to probability, as we understand it so far, sampling distributions in particular, and then a concept we have yet to get into in chapter 7 and 8. And so after 7 and 8, you might say, could you go back and relink the chapter 6 ideas to stuff we've learned in chapter 7 and 8? And we can do that, but I'm inclined to let the statistical process control content stay on its own. And so maybe I'll start lecture today with describing a story of a stat major who took a summer internship about 15 years ago. I'm forgetting his name, but I remember what he looks like. He had curly hair and a sort of super friendly guy, and he got a job working in a Dole salad processing plant in Salinas over the summer. So Dole, you go now, I guess you see different manufacturers. They sell lettuce in bags and they call it pre-mixed salad or pre-cut salad. And they pump some nitrogen in there to keep the product from spoiling. But the real idea is we've got this product here, and we want always the same amount to be put into every package. You could also view it like one of the examples is we've got these bolts with different possible diameters. If you use a micrometer to measure a bolt, hopefully you're going to have always exactly the same diameter in the bolt, because otherwise it's going to not quite fit on the nut. Okay. Or you can imagine if you're making welds and you're sort of watching this guy who's welding and welding and welding these little spot welds in aluminum, you want to make sure that, the welder is doing a fine job as opposed to getting really tired later in the day and doing a poorer job welding. And so we have a belief that there's a process that's going on. And if we observe the process from time to time, we can maybe spot changes in the underlying behavior of the if you will, the individuals or the machines that are generating the output. And if you can spot the problem soon enough, you could go in and say, okay, here's the sort of problem it is. Let's shut the plant down. We'll fix this problem and get back online. Or in the case of my friend, I remember the guy, Oliver, the curly-haired friendly stat major in Salinas. He said, there's a problem with this bag of lettuce packing machine. It's underweight now. It didn't used to be underweight, and now it is. And so he's spotting in the data a change in the behavior. And so we want to describe the process maybe with something like a distribution of possible values. So at time 1, let's go with this. And pick a color, go with black so I can see it nicely. At time 1, and I'm going to speak as though we have time periods that we're comparing. There are other ways of comparing across individual groups of data we could collect. They're sometimes called subgroups. You could lump them by the individual who did the job, or you could lump it instead of by time. You could lump it by, shift, morning, afternoon, swing. Okay. So, but I'm just going to say, well, what if it's across times of the day, and at time 1, there's a distribution of values that you could indeed observe from the process. Okay. And I'm thinking, let's just imagine filling a cereal box or filling this bag of lettuce. And sometimes, well, you're going to have quite typical values, like quite near mu. Sometimes mu, well, I guess if I rotate this sideways, this is mu plus 2 sigma and mu minus 2 sigma. And this is drawing it as if, and I'm not making this as a claim, but as if it's normal, this process. It doesn't have to be normal, but if it is normal at time 1, and then at time 2, I guess I changed my my font here, and I'm trying to draw this with the same mu, same upper and lower bounds for the plus or minus 2 standard deviation range. And if we're doing this across times, multiple times, different hours of the day, if you will, at every time, even up through time k, if the distribution has the same mean mu and spread, standard deviation mu plus 2 sigma and mu minus 2 sigma, you're thinking the process is in control. And that's the term we use, in control, if the distribution is constant. Same shape, mean, and spread. If any of those 3 change across time periods, I would say the process is out of control. Okay, so buzzwords, in control, out of control. It basically means we have something which we say we could do it again and get about the same distribution. Okay. So in control or out of control? Well, what sort of data would we likely see if the process was in control? I'm thinking to myself, well, let's go with a new color. I'll go pink so I can see it. You're going to see, if you see 4 data points, sometimes they're going to be low, sometimes high. Maybe they'll all be low. All 4 values might be low, or you're going to have, some far away, but some quite close to the mean. They're never going to be too far away from the average. The rule sampling distribution concept basically says the X bar at any time is going to tend to be about mu plus or minus 2 times then sigma over the root of the number of individuals you sampled. 2 standard deviations of the distribution of the possible sample means, up or down. And so I guess if I had information about where mu was, if I knew mu, and if I knew sigma, then I could tell you a range of values that are pretty darn likely to occur. Shoot, plus or minus 2 standard deviations. We could even go with plus or minus 3 sigma over the root of n is going to happen nearly always. And so our goal is, if we look at data that occurs naturally in time, do we see a way of estimating an unknown population mean mu? And do we see a way of estimating a standard deviation sigma? And from those estimates, can we get a range of values that are likely to be seen? And if we see something in our sample mean that's outside that range, then we say, problem, process is out of control. So I'm going to do a screenshot of this and then clear. and move on. And let's go ahead and sort of show you an example of the sort of data that you would have. There we go. And here's data on threaded stem diameters. I think they're supposed to be about 13 millimeters or so. And it looks as though this is 13.02, 12.95. If I tell you these diameters are supposed to be 13, you're saying, oh, they're all pretty darn close. The question is, across these different, and we'll call them subgroups, you could think the first hour of the day, okay? Second hour, first hour of the day, we're going to collect 1, 2, 3, 4, 5 of these diameters. Second hour of the day, we collect another 4. We get another 5. We get another 5. So each time we get an hour of the day, we're going to go grab these 1, 2, 3, 4, 5 threaded stems, and we're going to just measure the diameter with calipers. And we got, 25 separate hours of the day here that we're doing this. How would we handle this? Well, our software gives us this tool, and let's go with under Analyze. We're going to use a lot of fit Y by X this term. Sometimes we'll use fit model. I'm thinking under specialized models, okay, or quality and process, we see a few other things we'll do from time to time. Like we did see under multivariate, we said find the correlation. But under quality and process, let's just create a control chart, okay? And the control chart I want to use is sometimes called an X bar chart. Sometimes, if you will, you'll get an X bar and an R chart. We'll talk about the R chart in a little bit, but let's show you a quality control chart and X bar chart. I'm going to say I want to know about the diameters, boom, and my subgroups are defined by these numbers 1, 2, 3, 4, 5 up through 25. Just going to go ahead and click OK. And I see stuff given to me. What am I given? This X bar chart is upstairs. It tells me with this green trend line, if you will, the center line, this is the average across all of the data values. Okay, the average of all of the data values. This is the average of all the data values. Cool, got it. Then down, and I guess somehow we have these upper and lower ranges, and this is sometimes called the 3 sigma above, 3 sigma below limits, the upper control limits and the lower control limit, if you will, from our average green of 12.988. We're going to go up and down 3 times sigma over root n, and subgroups are of size 4, so it's sigma over root 4, sigma over 2, our estimate of sigma over 2. And we're going to get an upper control limit of 13.06, lower control limit of 12.91. If you ever are outside the upper and lower control limits, like we are here, here, and here, that's evidence that at least at these time points, or at these subgroups, the 3rd, the 18th, and the 25th, there's something unique going on, something that's different, quite different, in fact, than should have been happening if the process had been in control. Okay. So how do we estimate sigma? Well, I want to go back to history here. And this was invented by a guy named Schuhart way back when you didn't have the ability to calculate square roots easily. In our definition of the standard deviation, it involves the square root of n. So maybe a root of 2 would make some sense, but even finding the standard deviation, we're going to have to do a square root. And in 1930, square roots were not easy to calculate on a factory floor, even if you have only 4 data points. Okay. So Schuhart did some math, and he said, okay, if you just tell me the range, okay, of each and every data point, and that's what we're plotting downstairs, not every data point, but the range of each and every subgroup, like our range here was 0.1, the highest and lowest were 0.1 apart, or right here on the 6th subgroup, the highest and lowest were 1.17 apart. If you tell me there's variability in the ranges, cool, okay, I get the idea. There's a possible variability in the ranges. If you just tell me the average of the ranges, the average of the range we can work it backwards into an estimate of sigma. So we get sigma from our average of the ranges. We're going to talk about this R chart downstairs, the ranges, in a bit. But basically, the average of the range, this green line here, 0.1 or so, tells us a way of estimating sigma. And literally, the range average is not sigma hat itself. It's a way of getting our estimate of sigma. So we've got our individual means plotted from each and every group. Okay. We have where on average they should be and a range of values with our upper and lower control limits, UCL and LCL, that tell us whether we're out of control, like here, there, or not out of control. And these others might not be out of control. Okay. So what are the rules that we have for whether a control chart is out of control, indicating a lack of control in the process? Clear that. Okay. And let's go back here. Here are the rules for determining in control versus out of control. And literally, I guess I'm telling you the rules for when a process should be deemed out of control, when we'd say, okay, we need to go and do a little bit of extra work to determine if there is a problem, A, and then B, can we fix it? Okay. So one of the rules is any means outside the control limits. And the control limits are indeed, like before, there's a center line, there's 3 standard deviations above and 3 standard deviations below. So +3 and -3, -3. If we're outside the plus or -3 range, then you'd say we are indeed out of control. Okay. And again, this is +3 times sigma hat over the root of and the number of samples in a subgroup. So we call it +3 sigma, but really it's sigma over the root of n. Okay. So that's one rule. Here's a second rule, and this is sort of a fun one. Let's go with purple here. If I go 2 standard deviations above, +2 and -2, that defines a range which should happen, well, inside the range, +2 standard deviations. That's about 95% of the time. And so if 2 of 3 in a row, we have outside the plus or -2 range as defined here. So if we have 2 and a 3 outside that's 2 standard deviations above or 2 standard deviations below, you'd say, again, the process is out of control. I mean, plus or -3 sigma, if you're outside that range, that should happen only like 0.003 of the time, 3 out of 100 times. Even if you've got 25 data points, that should happen like 25 times 0.003. That's pretty darn rare. Shouldn't typically happen if the process really is in control. In that same sense, 2 out of 3 in a row is going to happen. How often? Like about as often, really rarely. And so if we see, say, a data point there, and then there, and then there, you'd say, aha, problem. We have 2 out of 3 in a row are outside the plus or -2 range. Okay, so let's get rid of that one, and that one, and that one. What about a third rule? Let's go with a different color and go green. +1 and -1. Okay, the green rule. 4 of 5 in a row are outside the plus or -1 range. So let's talk about that. If I have, say, 1, 2, 3, 4, 5, we would have simply violated that rule. 1, 2, 3, 4, 5. we don't see that very often. Indeed, it's going to happen about as often as you see something outside the control limits, or 2 out of 3 outside the ±2 range. So these are just frickin' approximate rules you could hand some guy on the floor of a factory who's pulling things off the line and just measuring things as they come down and say, well, this hour we saw 2 out of 3 outside the ±2 standard deviation range. Okay, let's look further. We'll deem the process is probably out of control. We'll try and figure out the nature of the problem. There are 2 more rules that I think our book will mention, but a friend of mine who is an expert in this downplays, so I'm going to sort of maybe choose another color. And maybe I'll move this here so I can see more easily. Rule 4, 6 increases, or if you will, decreases in a row. If you will, 7 values in a row that are going up, 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 up. So think 1, there. They don't have to be increasing in a linear way, but if it's always going up, 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 it says the mean is increasing across time. Similarly, if we had 6 decreases, or if you will, 7 points in a row that are going downwards from the previous, again, that's rarely going to happen just by luck. Rarely going to happen by luck alone. Okay. So what's the rule, the last rule? I'm going to go with 10, but this might be different than our book, but 10 alternating. Increase, decrease. So if you're there, oh, shoot, missed those. There. So notice the up, down, up, down, up, down, up, down pattern. 10 in a row that are alternating. You'd say, aha, that's a process that's out of control. It seems like there's a cycle of sorts. So let's look back at our example earlier and check these additional rules. Okay, drawings. What I have here in my X bar chart is I'm looking for 2 of 3 in a row outside that range. And the software will give you the option of just drawing it in, but I've got this already done. So I'm going to go approximately 2/3, 1/3, 1/3, 2/3. And I definitely see outside the range, we violate our control limits, but the 2 of 3 in a row outside the range, well, there's 1 outside the 2 sigma range. Well, there's another one. And the only ones that are outside the 2 ±2 range are outside the ±3 range. So we would have failed there already. What about the 4 out of 5 in a row outside the ±1 range? Well, I'm thinking 1, 2, then we're in the range, we're below in, so we don't hit 4 out of 5. In fact, there's no 4 out of 5 in a row anywhere that we hit. What about our friend 6 increases in 6 data points in a row going up, or 7 data points going up, up, up. Well, we've got a down, a down, a down. That's 4. Down, down. Okay, up, up, up. There is nowhere where we see 7 values in a row that are increasing monotonically. So we pass that rule. What about the alternating up, down, up, down, up, down? Well, we don't really see an up, down, up, down, up, down pattern that is 10 in a row. I see right there is 3. Down, up, and that's it. Down, up, that's it. So we on the top graph, we seem to only fail at these out of control points, these individual means that are so far away from where they should be that we're convinced something unusual happened at those time periods. Those same rules could be applied to not just the X bar chart, but also The R chart, the range chart. Now, I'm going to say there's a different set of mathematics that we would go through to get our control limits for the R chart. Here's the R chart. If I could use my pen, that would be good. R chart. The X bar chart is upstairs. The R chart, the downstairs thing, the lower control limit, sometimes is at 0. But always the upper control limit, you see L, okay, and then the center line, CL for center line, the upper control limit is always 3 away. Yes, 1, 2, 3. So we could again chop it by 2/3, 1/3, and that amount we could go down. And indeed here, if we go down 3, we'll get below 0. I guess that's not going to happen. But I can check, we could check here and see that we don't have a problem with going above the control limits, and we don't have a problem of 2 out of 3 in a row outside the plus or minus 2 range, or even 4 out of 5 outside the plus or minus 1 range. But it does look as though there's almost a strange cycling in our data. The 6 in a row, 6 increases in a row, we don't see that. But we do seem to have, for a while, a down, up, down, up, down, up. In fact, it almost looks as though there's something going on, but we don't ever have that down, up, down, up, down, up. Even towards the end of this series, where we have 1, 2, 3 down, 1, 2, 3 down, 1, 2, 3 down, 1, 2, 3 down, I don't see that preceded by the same pattern earlier. So it could be a case of a 1, 2, 3 step, 1, 2, 3, 1, 2, 3, but we don't know that for sure. The key is, if you tell me a certain sort of pattern is one that you would want to avoid seeing, we can devise a rule to spot that pattern. The control limits we really want you to sort of follow are those 5 I gave you earlier. I feel pretty good about this. I want to say that there's one other control chart out there. It's a P chart, okay, which looks at probabilities or proportions. The lab walks you through it. I have not paused. I've kept talking. I'm sorry. If any of you unmuted and tried to say anything and I didn't hear you, I apologize. Do any of you have questions about any of this, or should we wrap it up and tomorrow come back with questions related to Chapter 5 probability and then the exam that's turning live tomorrow night? Any questions on control charts so far?
Sorry, this was the R chart, correct?
Yeah, downstairs is the R chart and upstairs is the X bar chart.
Thank you.
And the lab walks you through yet another way of constructing these, as well as a P chart. But basically it's, oh, look, there's a pattern out of control. Oh, there is no pattern and we're passing every test, not out of control. It's something that students tend to find is really pretty chill. And they're like, oh, I can glance at that and see the issue, or that there is no issue. So does that answer your question, Jose, about the R chart downstairs?
Yes, thank you.
Anyone else?
So for the R chart, would you say that it is out of control because of the cycling pattern or no?
No, we need to see formally 10 up downs in a row, or you would need to talk to someone who said, well, what if it's a 1, 2 step, 1, 2 step, 1, 2 step, up, down, up, down, up, down. What sort of a pattern would you need to see? How many cycles of that would you need to see before you say, aha, there is something that happened? I would imagine something like the morning shift, the afternoon shift, the swing shift might have different overall quality results that you could get across those 3 different shifts on the work site. And if you tell me that's the pattern you're looking for, we'll construct a rule for you that would allow you to optimally spot the pattern you think is likely to be the problem. We're just scratching the surface with one day and that's it. If you really want quality control, there's whole on classes you could take. You could spend years studying this, and that's cool for folks that want to do that. I just wanted you to see it once, if none of you had questions about the exam or the probability. But you didn't have those questions, so we did this. Okay, any other questions? So what I'd love to do then is to say, okay, cool. I'm going to hang out and say nothing else, but I'm going to stop the recording and tackle questions you might have. I'm going to stop the share as well. Tackle any questions you have before bailing out of the room, but enjoy the afternoon and make sure that you focus more on prepping for the probability section of the midterm than on this lab. This lab is due on Monday. There's no rush to get it done. Focus on the exam, which is due by Saturday midnight. We'll see ya.